Hey everyone and welcome back. Now, if you've been following our journey into solar design, you might have caught our previous video on PV string sizing. And based on your feedback, it seems a few points might have left you scratching your head, especially when it came to real-world system sizes and mixing panels. Well, consider this video your ultimate clarification session. Today, we're not just reviewing the basics, we're diving deep, step by step, to unravel all the complexities of PV string sizing, from the absolute fundamentals to advanced considerations like temperature, multiple MPPTs, and yes, even how to handle different wattage panels without blowing a fuse. We're going to walk through exact examples for 5 kilowatt and 8 kilowatt solar systems, ensuring every single step is crystal clear. By the end of this, you won't just know string sizing, you'll master it. No more confusion, just confidence. Are you ready to design like a seasoned pro? Let's dive in. Section 1. The absolute basics. What is a string? First things first, what exactly is a string in solar? Imagine your solar panels are like individual building blocks. When you connect several of these panels together in series, positive terminal to negative terminal, just like batteries in a flashlight, you create what's called a PV string. This is crucial because when panels are in series, their voltages add up while their current stays roughly the same. Why is this important? Because that higher voltage is exactly what your inverter needs for efficient power conversion. So more panels in a string means higher string voltage. Simple, right? Section 2. Why string sizing is critical. The inverter connection. So why is string sizing so important? Because your inverter, the brain of your solar system that converts DC power from your panels into AC power for your home, has very specific electrical limits. Every inverter has an MPPT voltage range. MPPT stands for maximum power point tracking. This is the sweet spot where your inverter operates most efficiently, extracting the maximum power from your panels. Your string voltage must fall within this range for optimal performance. Then there's the maximum DC voltage. This is a hard limit. If your string voltage exceeds this, even for a moment, you risk damaging your inverter and nobody wants that. And finally, the maximum DC current. Your string's current must not exceed this value. While current typically doesn't change much within a series string, connecting multiple strings in parallel will add their currents, which the inverter must be able to handle. Incorrect string sizing can lead to poor performance. Your system won't produce as much power. System damage. Fried inverters are expensive. Safety hazards. Electrical overloads are dangerous. Section 3. The key parameters you need, panel and inverter datasheets. Alright, to size a string, you need two key documents, your solar panel datasheet and your inverter datasheet. Let's break down what to look for. From your solar panel datasheet, you need VMP, voltage at maximum power, the voltage where the panel produces its most power. VOC, open circuit voltage, the maximum voltage the panel can produce when no load is connected. This is crucial for checking the maximum string voltage. IMP, current at maximum power, the current where the panel produces its most power. ICE, short circuit current, the maximum current the panel can produce when its terminals are shorted. Pmax, maximum power, the rated wattage of the panel, e.g. 400 watts. Temperature coefficients, VOC, VMP, ISC. These tell you how voltage and current change with temperature. They're almost always negative, meaning voltage decreases as temperature rises. This is an advanced point we'll cover soon. From your inverter datasheet, you need MPPT voltage range, VDC, the optimal operating range. Max DC voltage, VDC, the absolute highest voltage it can handle. Max DC input current, A, the maximum current it can handle per MPPT input. Number of MPPTs, how many independent strings it can manage. Max input power, kilowatts per watt, the maximum total DC power the inverter can handle. Get comfortable finding these numbers. They are your best friends in solar design. Section 4. Step-by-step basic string sizing, no temp consideration yet. Let's do a basic example. For simplicity, we'll ignore temperature effects for a moment. We'll add that complexity in the advanced section. Panel 400 watt panel, VMP equals 40 volts, VOC equals 48 volts, IMP equals 10 amps, ISKI equals 10.5 amps, Pmax equals 400 watts. Inverter 5 kilowatt inverter, MPPT range equals 120 volts to 450 volts. Max DC voltage equals 500 volts. Max DC current per MPPT equals 15 amps. Number of MPPTs equals 2. Max input power equals 6000 watts. Step 1. Determine the minimum number of panels per string for MPPT range. Your string's VMP needs to be at least the inverter's minimum MPPT voltage. Minimum panels, Shugoth, inverter min MPPT VMP. Panel VMP. Calculation 120 volts divided by 40 volts equals 3 panels. So you need at least 3 panels in a string. Step 2. Determine the maximum number of panels per string for max DC voltage. Your string's VOC needs to be less than the inverter's maximum DC voltage. Maximum panels equals inverter max DC voltage divided by panel VOC. Calculation 500 volts divided by 48 volts equals 10.41. You must round down to the nearest whole number to be safe. So you can have a maximum of 10 panels in a string. Step 3. Check string current against inverter max DC current. The current of one string is roughly equal to the IMP of a single panel. String IMP equals 10A. Inverter max DC current per MPPT equals 15A. Check 10A is less than 15A. Good. This also applies to ISC against max DC current. Result for basic sizing. For this example, your string can have anywhere from 3 to 10 panels. You typically aim for the upper end of that range to maximize voltage and minimize current, which helps with efficiency. Section 5. Advanced string sizing. Temperature matters. Now, let's level up. Temperature has a huge impact on solar panel performance. Cold temperatures, panels produce higher voltage, VOC, and VMP increase. This is critical for preventing overvoltage on your inverter. Hot temperatures, panels produce lower voltage, VOC and VMP decrease, and lower current, IMP decreases. This can push your string out of the inverter's MPPT range, reducing power. This is especially important depending on your climate. Here in Saudi Arabia, where temperatures can soar, managing the voltage drop in extreme heat is crucial. But even in colder climates, you need to account for those frosty mornings where voltage spikes. You'll need 2 more pieces of information. Lowest expected ambient temperature, Tmin, the coldest temperature your panels will experience. Look up historical weather data for your location. Example for a colder region, minus 10 degrees Celsius, 14 degrees Fahrenheit. Example for Saudi Arabia or a very hot region might be more like plus 5 degrees Celsius in winter. Highest expected ambient temperature, Tmax, the hottest temperature your panels will experience. Example for Saudi Arabia, plus 50 degrees Celsius, 122 degrees Fahrenheit. Note, cell temperature can be even higher than ambient, sometimes by 20 to 30 degrees Celsius. For professional design, you'd use a Nocti calculation or add a temperature adder for roof-mounted panels. For simplicity in this example, we'll use Tmax as the maximum ambient. And from your panel datasheet, you'll need the temperature coefficient of VOC, TCVOC, usually expressed as percent per degree Celsius or millivolts per degree Celsius. It's almost always negative. Example, negative 0.30% per degree Celsius. You'll also need the temperature coefficient of VMP, TCVMP, also usually negative. Example, minus 0.40% per degree Celsius. Section 6. Calculating with temperature effects. Let's apply this to our example. Panel VOC equals 48 volts, VMP equals 40 volts, TCVOC equals negative 0.30% per degree Celsius, TCVMP equals negative 0.40% per degree Celsius. Inverter. MPPT range equals 120 volts to 450 volts. Max DC voltage equals 500 volts. Site, Saudi Arabia example. Tmin equals plus 5 degrees Celsius, coldest winter night. Tmax equals plus 50 degrees Celsius, hottest summer day. STC temperature, standard test conditions. This is where panel specs are measured, typically 25 degrees Celsius. Calculation 1, maximum voltage at coldest temperature for max number of panels. This determines the absolute maximum voltage your string will ever reach. Delta T, cold. See your T min STC temp. 5 degrees Celsius minus 25 degrees Celsius equals negative 20 degrees Celsius. VOC at T min, VOC yes STC, 1 plus TC VOC 100, delta T 48 volts, 1 plus 0.30 120, 48 volts, 1 plus 0.003 times 20 equals 48 volts, times 1 plus 0.06 equals 48 volts, times 1.06 equals 50.88 volts, times. Now calculate the maximum number of panels using this new VOC times max panels equals inverter max DC voltage divided by VOC at T min times equals 500 volts divided by 50.88 volts equals 9.82, round down. So max panels equals 9, previously 10, see how temp affects it. Calculation 2, minimum voltage at hottest temperature for min number of panels. This ensures your string stays within the MPPT range even on the hottest days. Delta T hot, T max, STC temp, 50 degrees Celsius minus 25 degrees Celsius equals plus 25 degrees Celsius. VMP at T max, VMP STC, 1 plus TC VMP 100, delta T, 40 volts, 1 plus 0.40 100, 25, 40 volts. 0.004 times 25 equals 40. V times 1 minus 0.1 equals 40 V times 0.9 equals 36 V. Now calculate the minimum number of panels using this new VMP. Min panels equals inverter minimum MPPT VMP. VMP at T max. 120 volts divided by 36 volts equals 3.33, round up. So min panels equals 4, previously 3, again temp matters. Revised result with temperature. Based on temperature extremes, your string can now have anywhere from 4 to 9 panels. This is a much safer and more accurate range for long-term performance and safety. Section 7, System Sizing Examples, 5 kilowatts and 8 kilowatts, and panel wattage. Let's put this into practice with real-world system sizes. Scenario 1, 5 kilowatt solar system string sizing using same wattage panels. Target system size 5 kilowatt, 5000 watts. Inverter 5 kilowatt inverter, same as before, MPPT 120 to 450 volts. Max DCV 500 volts. Max DC current 15 amps per MPPT, 2 MPPTs. Max input power 6000 watts. Panel 400 watt panel, same as before, VOC 48 volts, VMP 40 volts. IMP 10A ISC 10.5A TCVOC-0.30% per degree Celsius, TCVMP minus 0.40% per degree Celsius, times temperature adjusted string range, 4 to 9 panels per string. Total panels needed 5000 watts divided by 400 watts per panel equals 12.5 panels. Since you can't have half a panel, you'll need 13 panels to reach at least 5 kilowatts. Resulting in 13 times 400 watts equals 5200 watts, 5.2 kilowatts. This is a great match for a 5 kilowatt inverter with a 6 kilowatt max input. String configuration. We need to arrange these 13 panels into strings within our 4 to 9 panel range. Option A. If your inverter has 2 MPPTs, you could do MPPT 1, 7 panels within 4 to 9 range. MPPT 2, 6 panels within 4 to 9 range. Both are valid string lengths and the total is 13 panels. Option B, if you only had one MPPT or wanted one larger string. This configuration with 13 panels would exceed our max of 9 panels per string. So a single string of 13 panels isn't an option with this inverter. This highlights why multiple MPPTs are often beneficial. Important note on same wattage panels. For optimal performance, always strive to use identical panels within a string. Even panels of the same wattage from the same batch can have tiny variances, but these are usually negligible for series connections. The important thing is that their VMP and VOC characteristics are consistent. Scenario 2, 8 kilowatt solar system string sizing using different wattage panels. Target system size 8 kilowatt, 8000 watts. Inverter 8 kilowatt inverter, example MPPT 200 to 800 volts, max DC voltage 1000 volts, max DC current 20 amps per MPPT, 3 MPPTs, max input power 10,000 watts. Panel type A 450 watt panel, VOC 52 volts, VMP 43 volts, IMP 10.5 amps, ISC 11A TCVOC-0.28% per degree Celsius, TCVMP-0.38% per degree Celsius, times panel type B 350 watt panel, VOC 42 volts, VMP 35 volts, IMP 10 amps, ISC 10.5A TCVOC minus 0.32% per degree Celsius, TCVMP minus 0.42% per degree Celsius. Temperature considerations. Let's assume the same Tmin plus 5 degrees Celsius and Tmax plus 50 degrees Celsius for simplicity. Calculating string range for 450 watt panels. VOC at Tmin 52 volts. 1 plus negative 0.28 divided by 100 times negative 20 equals 54.912 volts. Max panels 1000 volts. 54.912 volts equals 18.2. So, max 18 panels. VMP at Tmax 43 volts. 1 plus negative 0.38 divided by 100, 25 equals 38.905 volts. Main panels 200 volts. 38.905 volts equals 5.14. So, minimum 6 panels. Range for 450 watt panels, 6 to 18 panels. Calculating string range for 350 watt panels. VOC at Tmin 42 volts. 1 plus negative 0.32 divided by 100 times negative 20 equals 44.688 volts. Max panels 1000 volts. 44.688 volts equals 22.37. So max 22 panels. VMP at Tmax 35 volts. 1 plus negative 0.42 divided by 100. 25 equals 31.325 volts. Main panels 200 volts. 31.325 volts equals 6.38. So minimum 7 panels. Range for 350 watt panels 7 to 22 panels. The pitfalls of mixing different wattage panels in series. This is a critical point. Never mix different wattage panels within the same series string. When panels are in series, the string's current is limited by the panel with the lowest current, IMP. If you put a 350 watt panel, IMP 10 amps, with a 450 watt panel, IMP 10.5 amps, the entire string will only produce 10 amps. You're losing potential power from the higher wattage panel. Even worse, if there's a significant voltage mismatch, the higher voltage panel might try to force current through the lower voltage panel, creating hotspots and potentially damaging the weaker panel over time. How to use different wattage panels if you absolutely must? Option 1. Separate MPPTs. If your inverter has multiple MPPTs, you can create strings of uniform wattage panels and connect them to separate MPPTs. For example, MPPT1 string of all 450 watt panels, e.g. 10 panels equals 4.5 kilowatts. MPPT2 string of all 350 watt panels, e.g. 10 panels equals 3.5 kilowatts. 3.5 kilowatts times total 4.5 kilowatts plus 3.5 kilowatts equals 8 kilowatts. This is the ideal solution for mixing wattages if multiple MPPTs are available. Option 2. Microinverters. Optimizers. These devices connect to individual panels and allow each panel to operate at its maximum power point independently. This is the safest and most efficient way to mix different wattage panels, as well as handle complex shading. Section 8. Practical tips and considerations. Beyond the math, here are some practical tips. Roof space and layout. Does your calculated string size physically fit on your roof, considering obstacles like vents, chimneys, and shading? Shading. Analysis. Even partial shading can drastically reduce each string's output. Consider using optimizers or microinverters for complex shading scenarios, or adjust stringing to minimize shaded panels in a series. Module mismatch. As discussed, try to use identical panels within a string. Mixing different models or ages can lead to performance loss, especially in series. Cable sizing. Higher currents require thicker cables to minimize voltage drop and energy loss, a topic for another video. Safety and disconnects. Always ensure proper DC disconnects and overcurrent protection fuses breakers are in place. These are critical for system and personnel safety. Future expansion. If you plan to add more panels later, consider how that might impact your string sizing now. It's often easier to add more of the same panels to an existing string or create a new string on an available MPPT. Section 9. Tools and software. While understanding the manual calculations is crucial, in the real world, engineers use tools. Online string calculators. Many inverter manufacturers provide free online tools. These are fantastic for quick checks. Spreadsheets. Excel, Google Sheets. You can easily set up your own robust calculator. This is great for custom designs. Professional design software. These are powerful tools for comprehensive system design, including detailed energy yield simulations, shading analysis, and advanced stringing optimization. They are invaluable for complex commercial or utility-scale projects. These tools automate the temperature calculations and factor in many other variables. But knowing the underlying principles helps you verify their outputs, understand the why, and troubleshoot any issues that arise. So there you have it. From understanding what a string is, to calculating your min and max panels with temperature compensation, and even tackling system-level sizing with same or different wattage panels, you're now equipped with the knowledge to approach PV string sizing with confidence. This foundational skill is absolutely essential for designing safe, efficient, and high-performing solar PV systems. If you found this video helpful, please give it a big thumbs up, subscribe for more solar insights, and hit that notification bell so you don't miss our next video. Let me know in the comments if you have any questions or what solar topic you want us to cover next. Thanks for watching and happy designing. See you in the next one.